So, can we please welcome to the Baobab stage Mr. Akiva Solemani.
Hello everyone, I'm Akiva. I was a maths teacher for 40 years, retired now. I taught in secondary schools and further education colleges and universities. I'm particularly interested in the history and philosophy of maths. And I'm particularly interested in this guy, Pythagoras, my favourite mathematician. I mean, I could talk about him for hours, but I think Tim would drag me off. Pythagoras was a Greek philosopher and mathematician. Now, philosophy in those days really covered everything. I mean, all the sciences, what we now call psychology, sociology, everything came under the word philosophy. He was born around 585 BC, over 2,500 years ago, on the Greek island of Samos. Here's a bust of him. Now, Bertrand Russell said of Pythagoras, "I do not know of any other man who has been as influential as he was in the sphere of thought." And Pythagoras was intellectually one of the most important men that ever lived. He lived in the same period as Confucius and the Buddha. They were all alive at the same time. Amazing period in history. He travelled extensively, learning from philosophers and mystics in Egypt, Babylon, India and Persia, as well as Greece itself. He became a revered figure, and many stories and legends grew around him. Many people regarded him as a semi-divine person. Now, he was so famous and popular and respected that even coins were minted with his image and name. He taught and believed in metempsychosis, or the transmigration of souls, a sort of reincarnation. The story is told of him telling a man to stop beating his dog because he recognised the voice of his relative in the dog's whine. This is mentioned in Shakespeare in Twelfth Night. Clown, what is the opinion of Pythagoras concerning wildfowl, Malvolio, that the soul of our grandam might haply inhabit a bird? The story is told of him passing a blacksmith and hearing him hit the anvil with hammers of different weights. Some sounds were harmonious, but one hammer wasn't. He went in and weighed the hammers. He found that the hammers that were in whole number ratios to each other were harmonious, but the other one wasn't. Now, this whole number bit is very important for his talk. From this, he worked out theories of music. Notes that are in whole number ratios to each other are harmonious. He found that if you halve the length of a string, the note goes up an octave. Now, the belief in those days was that the sun, the moon, and the planets were each embedded in the rim of a crystal sphere that rotated around the Earth. The fixed stars were all embedded together in one other sphere. Now, the sphere looked like one inside each other, rotating. Each sphere made a swishing sound with an individual note for each sphere. Because this sound was constant, people believed that it didn't register with people because it was always there. They weren't aware of it. They believed that only the master, Pythagoras himself, could hear it. Only he could hear the music of the spheres. You might have heard this phrase, the music of the spheres. Right, now, here's separate notes of each thing. I mean, it's represented on a piano. Obviously, they didn't believe there was a big piano in the sky, but it's represented on a piano, these separate notes, depending on how large the planets were, how big the spheres were, how far away from Earth it was. These were the notes. But of course, they were all going on at the same time, so it's like one big note. Now that, they believed, was the sound of the music of the spheres constantly in the background. Obviously, it's all rubbish, but that's what they believed. In mathematics, he discovered many theorems and was in the habit of sacrificing a bullock if he discovered a particularly important one. When he discovered the theorem that is still 2,500 years later known by his name, Pythagoras' theorem, he was so pleased he sacrificed the hecatomb, 100 oxen. That was odd considering he advocated vegetarianism. But But he realised the importance of that theorem for maths. This is Pythagoras' theorem. If you've got a right-angled triangle and you build a square on each side, then the biggest square is equal to the other two squares, the areas. So the area of the red square is equal to the area of the green square plus the area of the yellow square. And algebraically this is expressed a squared plus b squared equals c squared. The square just means the area of the square. For example, a 3, 4, 5 triangle would be a right-angled triangle. So the yellow square, 3 times 3 is 9. Green square, 4 times 4 is 16. The red square, 5 times 5 is 25. And you see that 9 plus 16 equals 25. Now, this is very useful in maths because if you know 2 of the sides, you can calculate the third missing side. Now, if the other 2 sides are 1 unit, well, the area of the yellow square would be 1 times 1 is 1. The area of the green square is 1. So that means that the area of the red square must be 2. 1 1 is 2. So if the area is 2, then the side of the square must be the square root of 2. The square root of 2 times square root of 2 is 2. That's what square root means. Now this is important, this square root business. This comes up later in the talk. Now, square root of 2 works out to be 1.44, goes on forever, and it doesn't repeat. Now, I've discovered a theorem myself, you know. If you've got a right-angled triangle and you draw a circle inside, where it touches the largest side, it splits it into 2 bits. Now, one bit times the other bit always gives you the area of the triangle. Now, I didn't want to be big-headed about it or anything, so I thought I'd just call it Solemani's theorem. Actually, I'm being a bit of an arsehole. I can't really call it Solemani's theorem. I'm sure over the centuries, lots of mathematicians have discovered this, but there's no record of it, and I did discover it for myself, and I did find the proof for myself. So, sod it, I'm going to call it Solemani's theorem. There you are. Who's going to sue me? Right, now I digress. Go back to Pythagoras. Pythagoras developed a cult following. He set up a group called the Pythagorean Brotherhood. Women joined as well, so perhaps it should be translated as a Pythagorean Fellowship. He was their master, their guru. It was virtually a religion, although the thing they worshipped was number. And that sounds very odd. How can you worship number? Well, Pythagoras taught that everything can be explained through numbers, through whole numbers, like the ordinary numbers, 1, 2, 3, 4, 5, 6. Whole numbers were like we regard atoms, as the building blocks of everything. Well, what about fractions? Well, fractions were simply the relationship between 2 whole numbers. The ratio of one whole number over another whole number. A whole number on top, a whole number at the bottom. That's a ratio, one over the other. So they believed that every number could be expressed as a fraction. So they believed that all numbers were rational numbers. Rational meaning could be expressed as a fraction. They had a sacred symbol, the 5-sided star, the pentagram. This is their sacred symbol. Now this star is made up from the diagonals of a pentagon. So if you have a pentagon, a 5-sided shape, if you join up the corners, you get the pentagram. Now the ratio of the diagonal of the pentagon to the side of the pentagon works out to be what is called the golden ratio, or the divine proportion. What is this golden ratio? Well, it can be derived from this. If you have a line, now what they believe the sort of aesthetically perfect place to cut that line will be such that the long bit over the short bit is the same as the whole line over the long bit. Right? So A over B equals the whole line over A. Now this, I'll spare you all the working out, all the calculations. This ratio is given the Greek letter phi. And phi works out to be this number. Take my word for it, it works out to be this. 1 plus root 5 over 2. And this number works out to be 1.61. Goes on forever, doesn't repeat. Now, you see why I'm mentioning this later. Now, this golden ratio can be applied to rectangles. The golden rectangle. So this would be the golden rectangle. Again, the A side over the B side is the same as both of them together over the long side. Now 5, this golden number, golden rectangle, has been used in many cultural areas for aesthetic reasons. For example, in architecture, Notre Dame, the Taj Mahal, the Parthenon and others have always used the golden rectangle ratio deliberately because they regard it as aesthetically pleasing. For example, here's a pictorial representation of what the Parthenon would have looked like when it was built. That's the golden rectangle. Many artists have used it. Dali, Da Vinci, Mondrian and others deliberately used the golden rectangle. For example, Salvador Dali, Sacrament of the Last Supper, that's the golden rectangle. Even composers have used the phi number in their works for the length of notes, the arrangement of the notes. Bach, in his Goldberg variations, Mozart, Beethoven, first movement of the Fifth Symphony, and others. Now, with their belief in whole numbers, the Pythagoreans believe that any two numbers are commensurable. What does this mean, commensurable? That means that any two fractions could be expressed with the same bottom number. For example, a half and a third. They could both be expressed as sixths. So half is 3/6, third is 2/6. So you could make any two fractions have the same bottom number. Another example, 2/5 and 3/7. You can have the same bottom number. Do you remember from middle school, common denominator, all that jargon? Just means make the bottom numbers the same. Then disaster struck. One of the Pythagoreans, one of Pythagoras' students, a smart-ass named Hippasus, discovered numbers that were not commensurable. He discovered numbers that could not be written as a fraction. For example, Hippasus proved that the diagonal of a square is not commensurable with the side of the square. In other words, he proved that square root of 2 can't be written as a fraction. So remember this, if you've got the side of the square of side 1, the diagonal will be square root of 2. Now you might think, well, surely you can draw a square where the diagonal isn't the square root of 2, but it's the ratio. It's like, if the side was 7, the diagonal will be root 2 times 7. If the side was 10, the diagonal will be root 2 times 10. So the diagonal is root 2 times whatever the side is. So, according to Pythagoras, the diagonal can be a fraction, should be a fraction, and the side should be a fraction, because he believed everything can be a fraction. Right? If they were both fractions, then they could be made to be fractions with the same bottom number. Now this is how Hippasus proved it. I won't go through all the calculation. This is the way he did it. From the big square, if I can explain this, in the big square, the diagonal's a fraction, the side's a fraction. You can make the fractions have the same bottom number. In the small square, which he constructed a special way, in the small square, diagonal's a fraction, side's a fraction. You can make them have the same bottom number. But he proved that the bottom numbers in the small square would be the same as the bottom numbers in the big square. But the top numbers would be smaller because it's a smaller square. And then even smaller square, even smaller, so smaller and smaller squares forever. So in every square, the bottom numbers are always the same, but the top numbers are getting smaller and smaller and smaller and smaller forever, and still being whole numbers, which is impossible. You can't have the top numbers getting smaller and smaller and smaller, and still remaining whole numbers, because eventually they're bound to become less than 1. Anyway, this meant that square root of 2 cannot be a fraction. Now, this was a dagger in the heart arising from Pythagoras' famous theorem. I mean, it doesn't mean that his theorem was wrong. His theorem is still absolutely right. All his theorems are absolutely right. But it destroyed his belief that everything could be expressed with whole numbers. What was even more disastrous, Hippasus proved the same thing with a sacred pentagram. Again, from the big pentagon, he drew a smaller pentagon off it in such a way that the diagonal and the side would have the same bottom numbers over and over again with smaller and smaller top numbers. So you can construct smaller and smaller pentagons forever with the same conclusions with the square. So he proved that square root of 2 and that number, which is 5, the golden ratio, he proved that both of them could not be expressed as a fraction. They were both irrational, which means can't be expressed as a ratio of one whole number over another whole number. In other words, they couldn't be expressed as fractions. Hippasus had discovered irrational numbers for the first time, which now, of course, in maths used all the time, we think nothing of it, but then it was shattering. Now, all decimals that come to an end can be written as a fraction. For example, 0.12 would be 12 over 100. All decimals that go on forever but have a repeated pattern can also be written as a fraction. So, for example, 0.333333 forever is exactly a third. But decimals that don't end and don't repeat cannot be written as a fraction. These are the irrational numbers. Now, for Pythagoras and his disciples, irrational had both meanings. The mathematical meaning can't be expressed as a ratio, and the common meaning, insane, irrational, crazy, madness, I tell you. Now, this discovery completely demolished the very foundation of Pythagoras' whole philosophy, that everything can be expressed with whole numbers. Pythagoras' brotherhood or fellowship fell apart. It was disbanded, and the Pythagoreans scattered. According to some historical accounts, Hippasus fled and was drowned at sea. Legend had it that he was killed by the gods for introducing the abomination of irrational numbers into the world. And some histories say Pythagoras also fled to Metapontum, is in southern Italy, it's part of Greater Greece at the time, and was murdered there in 497 BC at the age of 88. Oh, poor Pythagoras, my hero. How's the mighty fallen? Anyway, that's it. I hope you found it interesting.